Right. Hello, my name is Victoria and I'm going to be your TA this semester, if you haven't already met me. And basically this is just me running through that week 1 recitation guide just to get everybody up to speed, since this one is kind of a huge review, so something I thought we could cover online. So the first thing we're going to look at is this very first problem. This is something that should look pretty safe. We've got milliliters to liters. What's really cool about this is we can kind of use the prefix to kind of figure out what this means. So milliliters actually means 1,000. So milliliter means there's 1,000 of those per liter. And so when we want to convert them, we just do 250 multiplied by 1 liter divided by 1,000 liters. The other thing you can do is that you can simply divide 250 milliliters by 1,000 milliliters, but I like to do it this way so I can see these units cancel out and know that only liters is left. And so this is then going to equal 0, I need to draw, there we go, 0.25, and it's just selecting everything I do, hold on. There we go. No, but the one thing that we need to be mindful of is significant digits. So here we've got 4 sig figs, so to make this count up, we just add 2 zeros at the end. Remember to be mindful of your sig figs, okay? Next thing, write a formula for ammonium phosphate, sodium hydroxide, sodium nitrate, and water. I would definitely suggest not Googling anything. You don't want to be Googling it because it kind of takes away from you, especially if you're going to be taking a quiz and you've not seen it before, and it actually might be just something we made up and threw together, so even Google won't know. So I'm just going to do the one, ammonium phosphate, because for me this one is very tricky. So ammonium is written as NH4+, and again this is one of those polyions that I would remember, and I know that it has a positive charge on it because again there's a 5 electrons here to 4 protons here, so the difference of those is 1 plus charge, because in this case the nitrogens are positive and the hydrogens are acting as negatives. And then for phosphate I have PO3 3 minus, and that's good. And I simply just do this. I do a cross. There's 3 here, and then I know this plus is really a 1 plus, and so that just crosses over here. And so then when I rewrite this to be correct, I'm going to do NH4, and I know to balance there must be exactly 3 of them, and then I know that there's only going to need to be 1 phosphate ion. And you're just going to do that for sodium hydroxide, sodium nitrate, and water. All right. Next, we're just going to draw some Lewis structures, parent structures, and molecular shape, and then if it's polar or not. A lot of people get confused when they see parent structure. Parent structure is simply just taking the Lewis structure and then dissipating the electrons that we see, so those extra electrons. So for this Lewis structure, for water, we're going to draw our hydrogen. We know that hydrogen has 1 electron on it. We can see that in our handy dandy periodic table. I then know that I have an oxygen, as we can see in our molecule, and I know that it has 6, so 1, 2, 3, 4, 5, 6, and I know that I have hydrogen. So 1 hydrogen there. And I know that this also again has 1 electron. And I know to make a bond we need 2 electrons. So there's 1 bond and there's another bond. So then my parent structure will simply be this hydrogen connected to 1 oxygen, connected to another hydrogen, and then you're going to have 2 lone pairs of electrons on that oxygen. When you look at a molecule like water, when you're thinking of the molecular shape, we can think about how those 2 groups of unpaired electrons are affecting the bonding onto those hydrogens. So essentially they are pushing those hydrogens down because they're unpaired, they're very bulky, and so they're going to push the molecular shape in, and that's going to be something that's called bent. Okay. And finally, to answer this last question, if it's polar, when we think of water, because we have those hydrogens being pushed down and those extra little pairs of electrons that are unpaired sticking up like this, they are creating a dipole within them. So not only is there a dipole between the initial hydrogen and oxygen itself, but from the other one. And since those hydrogens are being pushed to the same side, it is overall polar. Okay? Now, do the same for carbon dioxide, ammonium, and also cyanide. Now, for number 4, when you're thinking of which of the following bonds is most polar, we're then just going to go back to our periodic table. When we look at the difference between, say, carbon and hydrogen, we can see that they're quite far apart. So we can think that so far, that one must be our most polar. When I look at carbon and nitrogen, they're quite close together. So this one is not as polar. So I'm going to say that so far it's still carbon and hydrogen. Carbon and oxygen, again, quite close. So carbon and hydrogen are still there. But we know the electronegativity of oxygen is much greater. And so since the electronegativity of oxygen is much greater, that is going to influence that this is a bit more polar. But then finally, when we think of oxygen to hydrogen, that is the biggest difference that we see, especially when we think that hydrogen is so small. Hence why we kicked it off the first place for carbon and oxygen. And so in that, this oxygen to hydrogen is definitely going to be our most polar. All right, and finally, we've got, if you had a sample of 150 grams, how many moles of hydroxide ions would be contained in it? So the first thing we're going to do is we're going to get this to moles of iron hydroxide. So I'm going to do 150 grams, and then I need the molar mass of this iron hydroxide. So I'm going to go to my periodic table. I find that iron is 55.8. I'm going to add that to 3 oxygens, which are 16 grams per mole, and 3 hydrogens, which are about 1 gram per mole. And when I do that, I find that the total is going to be 106.8. So I'm going to divide this by 106.8 grams per mole. And again, remember, this is of our iron hydroxide. And now I know that I have overall 1.404. 1.404. Because again, we have 4 sig figs moles of iron hydroxide. Now, when I look at iron hydroxide as a molecule, I then want to assess how many moles of hydroxide ions are in there. So when I'm writing it out now, I can see that when I count how many hydroxide ions, I have 3. And so I'm going to multiply this by 3 moles of that hydroxide ion divided by the 1 mole of that iron hydroxide. Because when we look at this, I have, if I were to decrease this down in, say, a chemical equation, I would see that there'd be 1 mole of iron plus 3 moles of hydroxide to 1 mole of iron hydroxide. Right? Okay. So when I do that, and I finish writing, I've done it again. And I've done that, then I know that I will have 1.404 times 3, which again, when we look down here, is going to give us 4.21 moles of our hydroxide. All right, so that's your first recitation. If you have any other questions or need help with any of the ones that I decided not to answer, just pop by my office hour or leave me an email. Thank you so much.